So in chapter number 13, we are going to talk about access control lists. This is kind of a brand new subject, a little bit different than everything else we've been talking about. Up to this point, we've been talking about the OSI model. We did a little bit with routing. We set up a basic routed network. We haven't done anything with static routing or default routing or dynamic routing yet, but we haven't done a whole lot with configurations. We looked at NAT and some other things, but our primary focus up to this point has been the OSI model. All right. Now we finished the OSI model, and we're going to start progressing into configuring different concepts and technologies throughout the network. Access control lists is one of those configurations. We use ACLs all the time. There are two primary functions for an access control list. Number one, access control lists are used to filter traffic passing through the network, pretty much as a security measure. We call that a stateless packet filter because it doesn't monitor traffic flows, it doesn't monitor a state table, it simply filters based on IP address, MAC address, potentially VLAN ID if you're doing some sort of ACL, or port numbers. There are many, many different types of ACLs. There are port-based ACLs, there are MAC ACLs. We have access lists that allow us to filter on VLAN information and so on. So think of an access control list exactly how it sounds, access control. Is this packet allowed to pass through the router, or is it not allowed to pass through the router? But that's not the only thing access control lists are used for. ACLs can also be used to classify traffic. Can anybody give me an example, and we saw it recently, in fact we saw it today, give me an example of how we used an access control list to classify traffic? I'll give you a hint. NAT. Do you guys remember? Access list 1, right? So when we use an access list to classify traffic, what we're doing is we're using that access list not to filter traffic, but to actually put traffic into a class so that we can apply a policy to that traffic, whether it is NAT, whether it's PBR, policy-based routing, or whatnot. We're going to look at both examples as we go through this chapter here. Now, what you're seeing on this diagram really is that first concept we talked about. Don't allow this, allow that, don't allow that, whatever. At different points in the network, we can apply these access control lists to either allow or disallow traffic to flow through the network. As a packet filter, we call these static packet filters, by the way, as I mentioned before, because we're filtering on static characteristics. I'm filtering on the protocol. I'm filtering on the port numbers. I'm filtering on the source IP, the destination IP, and so on. So as a static packet filter, I'm looking at criteria of the payloads that are coming through the router, and I'm making decisions. There are only two types of decisions that an access control list will make. Two decisions. Number one, is the packet permitted? Number two, is the packet denied? Am I allowing the traffic to flow, or am I not allowing the traffic to flow? So every access control list is a sequence of these access control entries. Now, we're going to talk about a lot of different rules about access control lists as we go through this chapter. But an access control list is a sequential list of statements that either deny or permit traffic based on matching criteria. The first rule that we learned, though, is that traffic that is generated by the router itself is never processed through an ACL that's attached to that router. What kind of traffic might you generate from the router itself? If I have a router here and a router here, and those guys are connected with a serial link, and I have an access control list, maybe there's an Ethernet network here, an Ethernet network here. I have an ACL applied in that direction. That can filter traffic coming from this network, but it would not filter traffic coming from the router itself. What kind of traffic would be coming from the router itself? Any ideas? What about things like EIGRP? Router protocols, talking back and forth. What about CDP? What about DHCP if the router is getting an address or sending an address to a destination, right? The router is acting as a DHCP server. So traffic originating on the router itself is never filtered by an access list that's applied to that router. It might be filtered down the line, but it's not filtered on that router itself. As I mentioned before, access control lists don't necessarily mean we're filtering traffic. Here's an example. I've got a router that's running NAT. I've got my inside, my outside interface. We talked about configuring NAT, all right? Maybe I'm doing port address translation. So what am I going to do? I'm going to have an ACL, we'll call it 10, to match the PCs, match my hosts. Okay, these hosts are over behind this network. Then my NAT policy says go ahead and NAT if the traffic is matching access list 10. So we're not actually using the access list in this case to filter traffic. We're using the access list to match a policy. I'm going to show you guys more about that later on when we start to look at some configuration examples. If I set up a lab, this is a question from online. If I set up a lab and do my ping from the router, it will never get filtered by that ACL. Yes, that is true, as long as the access list is on that router itself. All right? It might get filtered from an ACL that's on another router down the line, but not the router itself. All right? Explains a lot of my faults. Yep, a lot of people don't realize that. But Cisco did that for a reason, because a lot of engineers that are implementing basic configurations, they don't understand maybe that EIGRP requires specific port numbers or specific protocols to be open. OSPF, CDP, if it's a switch, RTP, and so on. Not RTP, STP. So rather than have to create an access list to allow all these things, Cisco said, well, if the traffic is originated from the router itself, we're not going to put it through the access list. When we're using an ACL to classify traffic, what does a permit do and what does a deny do? Let me give you an example. Let's say, let me open up Notepad here, and let's say I said access-list 10, deny host 10.10.10.10, and access-list 10, permit 10.10.0.0.0.255, and then IPNAT source, IPNAT inside, source list 10, interface E0, overload. Okay, we already know that source list 10 in this case is referring to access list 10. So if I have a network, if my network looks like this, right? Here's my network. Here are the 10. Here's the 10 hosts. Here's the internet. Here's my Ethernet 0 interface. If the traffic is coming from 10.10.10.10, when it hits this interface, what is it going to do based on that policy? It's not going to deny the packet. It's going to deny the packet from being translated. Because the access list is not being applied as a filter, it's being applied as a classifier. So to say I'm going to deny the traffic here means I'm simply denying it from being classified, which means that the packet does not get, or that packet does not get translated. We did not apply this access list to an interface. We applied the access list to a NAT process. So by denying that packet in the access list, we're simply saying, don't translate this host. And then by permitting the rest of the subnet, we're saying, go ahead and translate the rest of the network.
So if you were to send out a 10.3 deploy, the source is 10.10.11.10, it would get translated as well?
If the source was 10.10.11.10, it would also not get translated, but that's for a different reason. We'll talk about that in a little bit. All right? Now, Derek has a question. He says, what does that mean if it doesn't get translated? Well, it actually doesn't mean a whole lot. The packet essentially gets routed. Remember, when translation doesn't occur with NAT, the router doesn't drop that packet. It will still try to route it. And if there's actually a route to the destination, it'll send the packet. But it also probably means that the packet's not going to be allowed by the ISP because it's coming from an RFC 1918 address. And service providers monitor for that because they know that that traffic is not routed. Why are they going to waste all their bandwidth trying to route a packet that I can't respond to because it comes from a private address? The key that I want you to understand with this topic, though, is that when you're using an access list as a classifier, a deny means don't classify it. A permit means to classify it. Does that make sense? Okay. If you guys ever choose to go on and get your CCNP, also one of my favorite classes to teach, but if you go on and get your CCNP, you'll learn all about policy-based routing and route manipulation using things like route maps, prefix lists, distribute lists, and access lists. All right. No, the CCNP is a 9-day course. Okay. It's a little bit more involved, though. And it's nine days of basically 11-hour days. It's pretty intense. Okay?
Is the CCNP involved configuration?
Absolutely. In fact, almost 80% of the CCNP is configuration. Yeah. All right. We don't talk about things like the OSI model and, you know, subnetting and all that. We assume that you already know all that. So if you were to take a CCNP at somebody else's school, it would probably take you 3 weeks because they teach them as separate courses. There's actually 3 separate courses. There's route, there's switch, and there's T-shoot. But we've customized a class to be able to complete it in 9 days. We started on a Saturday, we ended on a Sunday. So it's still only 1 week, but you get those extra weekends on the sides to finish it up. It's a very fun class, though. It's pretty intense, but it's a lot of fun.
What did you say was that? Routing?
Troubleshooting.
Oh, troubleshooting.
Yeah. We call it T-shoot, but it's troubleshooting.
Okay.
Tissue? Yeah. Well, some people need tissues after that. All right. Okay. So, the raw syntax, right? Now, I hate looking at raw syntax. I like to look at actual examples because it makes more sense, practically speaking, if I can apply an example. But we do need to kind of talk about the different types of access control lists that you can have. By the way, ACLs used to be part of ICND2. We moved it to ICND1 because it's more heavily covered on the first exam than it is on the second exam. But this is actually one of those topics that is covered on both exams, so it's important. Two types of access lists that you'll see, standard and extended. All right, now we're talking about within IP. There are many, many types of access lists that you can create. But within the IP realm, we have standard and extended. Standard access lists can only filter on one thing, and it's listed in green right here, the source of the traffic. When I say source, what am I referring to? Source IP. So a standard ACL can only filter on where the traffic is coming from. An extended ACL can filter on all of these things. It can filter on the protocol, TCP, UDP, EIGRP, ICMP, BGP, etc. A lot of P's, okay? It can filter on the source IP. It can filter on the source port numbers. We're talking about layer 4 ports. It can filter on destination IP. It can filter on destination ports, and it can even filter with different options. So as you can see, an extended access control list provides you a lot more capability when it comes to filtering. A lot more capability when it comes to filtering. 99% of the time, your filtering ACLs are going to be extended, and most of the time, your classification ACLs are going to be standard. I'll explain why that's the case in a little bit. So, in general, we have two types of ACLs that we can create. A standard ACL that allows us to filter on the source address, and extended ACL that allows us to filter on a bunch of other things, including the source address. In addition to what we can filter on, by the way, we don't have standard ACLs for IPv6. In IPv6, you can only filter using extended ACLs. In addition to the classification, whether it's a standard or extended ACL, we also have the ability to type out the access control list using our legacy method, or to type out the access control list using what we call the named method, or more importantly, what we would call the modern syntax. Hey, if you want to grab, I have an extra power supply back there for the laptop if yours isn't working correctly. Yeah. We're going to look at examples of all of these guys, and just like we did with subnetting, there's math involved with this. I'm going to show you how to do wildcard masks, bitwise masking, etc. So there's a lot of stuff that we're going to be looking at as part of this discussion. The thing about an access control list discussion is it's a layered discussion. You have to get piece by piece by piece, and then you have to kind of see it applied, and we're going to do that. We're going to spend actually a little bit of time doing that. When it comes to creating access lists in a router, we do have some other rules. We call the 3 Ps rule. The 3 Ps rule means you can only apply one access list per interface. Where's my per interface? There it is. Per interface, per protocol, per direction. Those are the 3 Ps. So if this is Ethernet 00, I can only apply one IP access list in the inbound direction and one IP access list in the outbound direction. What do I mean by per protocol? What do we mean by per protocol? Per protocol means IPv6, IPv4, IPX, not TCP, not UDP, not HTTP. We're talking about protocol stacks. So I could have an inbound IPv6 access list and an inbound IPv4 access list, but I could not have two inbound IPv4 access lists. All right?
Would that be something that, at the router,
Yeah. Well, it wouldn't reject it. It would just replace it. So when you put in the command to apply the access list to the interface, it would just simply replace the other command that was already there. I'll demonstrate that when we do the configurations later. Also, when we talk about direction, it's from the perspective of the router. Direction is from the perspective of the router, not the network. So inbound is coming into the router, outbound is leaving the router. Some people get confused. They think from the perspective of the host, and that's not always the case. Well, it's never the case in the terms of an access list. Okay? So we have IPv4 ACLs, standard and extended. You guys remember what we could filter on with standard ACLs? What are we allowed to filter on with a standard ACL? Source IP. That's it. So I am permitting traffic, and I'm not worried about the syntax right now. We'll get into the syntax a little bit later. I am permitting traffic if it comes from this network. I am permitting traffic if it comes from this host. I am permitting traffic if it comes from that host. How do I know, using the traditional method, if it's a standard ACL? Because we have predefined numbers that define that it's a standard ACL. When you say access list 10, that means you're creating a standard ACL, simply because it is using the number 10. 10 doesn't mean a line number. 10 means an access list number. 10 means an access list number, not a line number. Okay? So these are called ACEs. The access list is 10 with 3 ACEs. Extended ACLs, those are going to have 100 to 199, 2,000 to 2699. What can I filter on with an extended ACL? Protocol, source address, destination address, port number. Again, the point of this slide is not the syntax, so don't worry about the syntax. We're going to get into the syntax in a little bit. The point of this slide is this. If the number of the access list falls from 100 to 199, it's an extended ACL. If it falls from 1 to 99, it's a standard ACL. Honestly, though, we don't really use the numbers anymore. Most of the time, we try to create these things called named ACLs, which is a more modern approach to implementing an access control list. Okay? Here's an example of a named ACL. Notice that the name, we can just specify whatever name we want, but prior to the name, we specify whether or not it's an extended ACL or a standard ACL. Again, I'm going to go through several examples. By the time I'm done with my examples, you should have a pretty good idea. In IPv6, we don't do standard. We don't do numbered. The only way to create an access list in IPv6 is with an extended named ACL. Now, the other thing you'll notice here is the masks that are defined. These masks look kind of strange, don't they? 0.0.0.63, 0.0.255.255. Actually, what those masks represent is something called a wildcard mask. We're going to spend probably about 20 minutes talking about the concept of wildcard masks. In IPv6, we don't use dotted decimal masks at all. So there's no concept of a wildcard mask because we just use prefix notation. All right? This might seem foreign. This configuration that you see here might seem foreign, might not make a whole lot of sense, But trust me, when we get to the point where we start to talk about syntax, we start to talk about configuration, it will make more sense. I promise you. Okay? Trust the process here. So what the heck is a wildcard mask? The wildcard mask is different than a subnet mask. It's actually very different than a subnet mask. Most people look at a wildcard and they say, oh, the wildcard mask is just an inverse mask, meaning it's the opposite. Whatever was a 1 in the mask is a 0 in the wildcard. Whatever is a 0 in the mask is a 1 in the wildcard. That's actually not true. But I will say this. If the bit is 0 in the mask, the corresponding bit value in the address means I care. 1s mean I don't care. Okay, what the heck does that mean? That's a rhetorical question. Okay? Wildcard masks are often referred to as an inverse mask, but they do not have to be. All right, here we go. Here is our access list mask review. There are two things that people get generally confused about when it comes to access lists. The one thing people get confused about is the syntax, just the general format. And that's something you just have to learn over time, this format of a mask. The other thing that people get confused about with access list, though, is how the masks are written. That's what people really get confused about. All right. Now, we do have some slides on this, but I have found in the past that doing an interactive discussion is often more conducive to learning the process. So let's start off with some very basic matching conditions. Permit 10.10.10.0, 0.0.0.255. Okay? This is probably one of the simplest match conditions that you'll see. This is an example of what I'm putting spaces in there so you can kind of differentiate. This is an example of what we saw like with NAT, right? Here is the inverse mask or the wildcard mask. What did we say about zeros? That means I care. What did we say about ones? I don't care. So what is going to be permitted by this rule? Any IP that starts with 10.10.10. Because the first 3 octets in the address are an exact match. The last octet, I don't care. You see what I'm saying? You guys agree with that? Okay, we need to make sure everybody agrees because, trust me, it gets more complicated from this point forward. Everybody agree with that? So what if I did something like this? 255.0.0.255. That is a perfectly valid matching mask. 0 through 255 in the first octet, 10.10.0 through 255, whoops, 0 through 255 in the last octet. Do you guys agree with that? I don't care about any of the bits in the first octet. I don't care about any of the bits in the last octet, but the middle 2 octets have to be an exact match. Yes? Do you guys agree with that? Okay. You guys online as well, if you're lost, let me know. Because access lists are something that we use all the time. And understanding the masking portion of an access list is really important. All right? By the way, this applies to routers. ASAs don't use inverse masks. They use regular masks.
Right, so with wildcards, you can do this, or,
You can do any combination you want.
so they don't necessarily have to be like,
That's exactly right. The wildcard masks do not have to be consecutive ones and zeros. All right? That's the one thing that people don't realize about a wildcard mask. Almost always they're written that way because generally the matching conditions that we're applying, we're not going to do something like this with a wildcard because we don't really have conditions that match this. You see what I'm saying? In a real production environment, I would never say, okay, allow everything that has the middle two octets of 10.10.
yeah.
You see what I'm saying? So in the real world, we do tend to see consecutive zeros followed by consecutive ones, but wildcard masks in access lists don't have to be that way. Derek has permit 1, deny 0. I'm assuming you mean in the mask. 1 means I don't care. 0 means I do care. If the address has a 1010 in the second and third octet, it will be permitted even though the corresponding max is 00. So the better way to say it would be, if it's a 0 in the mask, the corresponding bits in the address have to match the packet in order for it to be permitted. All right, let's get a little bit more crazy here, because this is actually something you would see kind of common. 10.10.10.0, 0.0.0.3. Everybody knows, or you should know, that the packet, in order for it to be permitted, would have to start with 10.10.10. You guys agree with that? Any bit difference in the packet going through the router in those first 3 octets means the packet would be denied. But what about the last octet? What am I going to be matching in the last octet? That's right. Well, the last 2 bits I don't care about. So here's how we interpret this. Look at the address. The last octet is a 0. From a binary perspective, that means 0, 0, 0, 0, 0, 0, 0, 0. Do you guys agree that that equals 0? And what does 3 equal to? 0, 0, 0, 0, 0, 0, 1, 1. You guys agree that that equals 3? What does that mean? That means that the last 2 bits in the address don't matter. 1s mean I don't care. 0s mean I care. Which means that as long as the network, the address falls between what and what? 0 is not going to match. Actually, 0 would match, wouldn't it? 0 through what? Not 0 through 3. Is it 0 through 3? Yeah, it is. Right? Because these bits here cannot change. And that's based on what we had here. What if I change that to 16? What if I change that to 16? Now, this bit is a 1. Agreed? So now, what's our match condition? 16 to 19. Because this bit always has to be a 1 because the corresponding bit in the mask is a 0. So that would match 16 to 19. Why? Because these bits can be anything. We don't care what those bits are. So it could be, the address could be 0001, 0001, or it could be 0001, 0010, or it could be 0001, 0011. You see what I'm saying? I don't care what the last two bits are based on that wildcard mask. You all right back there?
Yeah, I'm trying to calculate the 0001, 0001.
Well, this is 16 plus 1, 16 plus 2, 16 plus 3.
Yeah.
And the reason why I can change these last two bits and have the packet still be permitted is because the wildcard mask bits are 1, 1 there. Remember, in the wildcard, a 1 means I don't care what the bits are. A 0 means whatever the bits are, they have to stay that way. You see what I'm saying? Now, what's interesting is you can do this in many, many different ways. I could say 1.0.0.3. We're being very creative now, but what does the first octet match? And that's the other thing, by the way, to think of. When you're doing matching and access lists, it's always done octet by octet by octet. We're not matching a whole address. We're doing what we call bitwise matching, meaning we're matching individual bits in the mask to individual bits in the address. So what does the first octet match? Any ideas? We know that the address is 0001, 010, right? That equals 10. We also know that the wildcard is 00000001, which equals 1, which means I don't care what the last bit is, which means it matches 10 and 11. So as long as the first octet of the packet is 10 or 11, we're going to permit that packet. Well, we have to look at the rest of it, right? What's the second octet match condition? It has to be exactly 10. What is the third octet match condition? It has to be exactly 10. And here, let's make this a little bit more interesting. 7. Well, 16 is 00010000, and 7 is 00000111. So the third or the fourth octet is going to match what? It's going to match 16 through 23.
Now, going back to the concept of the wild card to be
all right, so the question was, and that's the next step, what if it's not consecutive zeros and ones? What if it's a 5? Heck, what if it's a 200? What if it's a 12? What if it's a 20? Okay, well, let's look at that. If this is a 5, which, by the way, is allowed. When I did my CCIE routing and switching lab with Cisco, one of the tasks that I had to do was to redistribute routes from one routing protocol to another. And I had to do it using a route map and different policies. But they said I had to redistribute these specific subnets. And I had to do it in a way that I only could use a one-line access list. So I actually had to do the bitwise calculation to figure out which bits would match those subnets so I could do the redistribution. So let's see, what's 16? 0001, 0001, 0, 0. That equals 16, right? What is 5? 0, 0, 0, 0, 0, 1, 0, 1. That equals 5. Does everybody understand how I got those two numbers there?
Yeah.
So what are my matching conditions? Does 16 match? Yes. Does 17 match? Yes. Because I don't care what this bit is. You see what I'm saying? Does 18 match?
Yes.
No. Because in order for the number to be 18, this bit would have to be changed, to a 1. That bit cannot be changed to a 1 because the corresponding bit in the mask is a 0. See what I'm saying? Does 19 match? No. Because 19 still means that that second bit would have to be changed. Does 20 match? Yes. Because this bit is allowed to be changed. You see what I'm saying? And of course, 21 would match as well. So 21 would match. 22 would not match. You get the idea. Whatever corresponds to a 1 in the mask, whatever bit in the address corresponds to a 1 in the mask, I can change those. I don't care. But if the corresponding bit is a 0 in the mask, whatever the value is set, and when I say set, I mean in the match condition, whatever value is set has to stay that value. You follow me? So actually, it doesn't matter. You could have 1.12.34.5. How do I evaluate that? I simply look at it octet by octet. Now, this would change, by the way, in that scenario. I'm going to explain that in a minute. But the bottom line is you simply look at the bits. Whenever there's a 1 in the mask, I don't care what the bit is in the address. Whenever there's a 0 in the mask, the bit in the address has to stay that value.
Or like when we, for the first section of it, the source, like the 10.10.
That's the matching address, yes.
Yeah, the matching address. Does it necessarily have to be a value that isn't matching any of the wildcard bits? Like for example, when we had the wildcard bits for 5.
Yep.
Instead of having 16, would it be okay to have 20 or 17?
As the starting condition?
Yeah.
Okay, let me explain. Let's go through that process. So he said, what if I did 10, 10, 10, 20 and 0.0.0.5? Okay? Is that allowed? Okay, well, let's look at how that converts. 20 is 0.0.0.1, 0.1.0.0. You guys agree with that? 16 plus 4, right? You guys agree with that? Okay? 5 is 0.0.0.0.1.0.1. That equals 5. So what's going to happen when you put this command into the router is it's going to change the 20 to a 16. Because it said 20 is already included, but that's not the first possible value. It drops all of the all the bits that correspond to 1 to their least common denominator, which is a 0. Does that make sense? So even though 20 is included in the match conditions, it's not the first possible match. So you could type in this command in the router, but when you do a show run, it'll have converted that to a 16. Because 20 falls within the range, here's one of the don't care bits, here's the other don't care bit. Even though 20 falls in that range, it's not the first possible match condition. Everybody online is very quiet right now. Usually people are asking questions and saying things. But, all right. Make sure they're still there. Yeah. Probably not a good topic to do at 3 in the morning when you're drinking wine. Right. But that's why we're recording it, so you can go back and see it a little bit later on. Does it at least, I mean, look, you probably have to look at this a few times to really understand it, but hopefully it gives you a better understanding of how these match conditions work. Now, in reality, what are you going to have to know for the exam? The types of match conditions you're going to see on the exam are stuff like this. Of course, that wouldn't be a 16 anymore. That would go to a 0. You're not going to have wild cards on the exam that are, you know, crazy wild cards like we've been looking at. You might see something like a 63 or a 15 or something like that. Wouldn't the ACL give out a warning when you put in, when it changes your IP? No, it doesn't. It doesn't give you a warning at all. Now, there is the possibility that you could put in something that's invalid completely. Like there's no way to match those conditions, and then it might give you a warning or it might not allow you to do that. But the router pretty much decides for you what that entry should look like based on the least common denominator of the match conditions, the very first match. All right. So here's just some examples. These are very simple examples. What does a 0.0.0.0 mean in the wild card? All zeros mean an exact match, meaning all the bits have to match in order for the condition to be met.
Would that necessarily mean a host?
It could mean a host, yeah, or yeah. Well, in this case, it would mean a host, yeah.
Now,
not permit all. It's not permit any because it's an exact match. Permit any would be all 255s. Yes.
Now, with so the syntax that you have there, it's okay to write all three. Whether we do the.
Well, actually, that's a good point. Thank you for pointing that out. The syntax here gives you an idea of how it can be written. You can write it like this, or like this, or like this. In a standard ACL, if you just put an address instead of without a wildcard, then the router assumes you're talking about a host. Okay? The router assumes you're talking about a host. So you guys look at this, dang it, you guys look at this and, you know, it has to be 192, it has to be 168, it has to be 10, it has to be 50. All right? What about this example? 10.0 with a wildcard of 0.0.0.255. Well, that's simple enough. The last octet, we don't care. By the way, in these examples, anything that's red means I don't care. I don't care what those bits are. And by the way, the mask can be, as we've already seen, any combination. I don't care about the first octet. I don't care about the last octet. What about this example? This is where we start to get into some of the interesting things, right? 192 with a 63, meaning these bits, the last 7 or 6 bits, we don't care about. The first 2 bits are fixed at 1, 1. So it's going to match anything from 192 to 255. In the second octet, it's an exact match. In the third octet, it's 10. With the last bit, I don't care, so that bit can be a 0 or 1, which means 10 or 11, and so on. This example at the bottom of the page is the wrong format. You cannot start with 10 with a match of 7. Why? Because 10 includes what? 8 and 2. But 2 is in the bits I don't care about. So what is the 10 going to get converted to? It's going to get converted to an 8. Because these 3 bits I don't care about. That bit has to be a 1. Does that make sense? Doesn't make sense. Why was the 37 converted to a 32? Because with 37, those bits I don't care about. So the router says, what's the least common denominator? It's the 32. So I'm going to go ahead and convert that to a 32. Questions? Okay. We're not quite done. We still have to look at the configuration. We still have to look at some examples, and we still have some rules to learn about. First rule that we learn about is that access control lists are processed from the top down. What does that mean? Access control lists are processed from the top down.
Whichever rule the packet matches first will be applied.
Yes. Access lists are a list of rules in order. Rule 1, Rule 2, Rule 3, Rule 4, Rule 5. When we process the packet through the list, we start at the top. Does this packet match Rule 1? Does it match Rule 2? As soon as there's a match, we do whatever that match says. We either permit the packet or we deny the packet. It is possible for a packet to match multiple rules. It could match Rule 1 or match Rule 5, whatever. Make that 5. But as soon as the packet matches Rule 1, we do whatever that rule says. And we stop processing that packet through the list. So that means your most specific rules go to the top. For example, why would I ever do something like this? Permit 10.10.10.0 and then deny host 10.10.10.10. I would never do something like that, would I? Because the host is going to get permitted by the first rule. And actually in the new syntax or the new ILS, the router actually doesn't even allow you to do that. It tells you, no, you can't do that. You have a better rule at the top, or you have a matching rule at the top, which would negate this rule. So we always put our more specific rules at the top of the access list. Put your more specific rules at the top of the ACL. This is probably the most important rule for an access list that you can remember. There is an implicit deny at the end of every access list. What does that mean? If the packet is not explicitly permitted by a rule, it will get denied. Remember you were talking about earlier, if I had NAT conditions that said deny host 10.10.10.10 and then permit 10.10.10.0, 0.0.0.255, and I applied that to a NAT policy, what about 10.11?
Yeah.
10.11 would get denied. It would not be natted because there's an implicit deny everything else at the end.
Oh, okay, but it would still get routed.
It would still get routed, it just wouldn't get natted. Question from online. Can I set up a syslog that if X tries to do something that my ACL doesn't allow, I get a syslog on my PC? Yes, you can. You have to be careful with that because generally access lists do deny a lot of things. So you can overwhelm your router or you can overwhelm your syslog server with a bunch of information. You can also do logging directly on the ACL. We'll see that a little bit later on. Every ACL has to have at least one permit, because an access list without a permit denies everything, right? I mean, if there's an implicit deny at the end and there's no explicit permit anywhere, then of course everything gets denied. Where do I place my ACLs? This is an interesting concept. Place your access control lists where they have the greatest impact on efficiency. Extended ACLs always go as close to the source. Standard ACLs always go as close to the destination as possible. It's not for distribution purposes. I have a pretty diagram that allows me to describe this concept. Let's say that my goal in this case is to block traffic from the 10 subnet to the 30 subnet. My goal here is to block traffic from the 10 subnet to the 30 subnet. Now let's say I applied a standard ACL here. Forget the ones over there on the right. I put a standard ACL here, thinking, well, let's go ahead and block that traffic that's close to the source. What does a standard access control list filter on? What does a standard ACL filter on? Source address. So by placing a standard ACL on this interface in the inbound direction, what have I effectively done?
Blocked all the traffic that's going
anywhere.
Yeah.
The 10 subnet wouldn't be able to go anywhere because I'm blocking based on the 10 subnet. So my only option would be to place that access list here in the outbound direction. But that's a waste, isn't it? I'm now routing a bunch of traffic across my network that eventually is going to get dropped. But if I define my access list with only source information, that's the only choice I have. Conversely, if I create an extended ACL, guess what an extended ACL matches on? Source, destination, port, protocol. So by placing an extended ACL inbound as close to the source as possible, there are no other possible match conditions because the traffic has to be coming from here, going to here, using these protocols. The only packets that will match that are the packets that actually do that. It's better to use extended ACLs and apply them as close to the source, because why do you want to waste bandwidth when you know the traffic's going to get dropped? And because the match conditions are so specific, they will only match that specific flow that you determined, they're much more efficient. All right. So we got a few more things to do here, and we'll wrap this chapter up. We got to learn how to configure access lists, and then we also have to learn how to verify them. So let's take a look at this example. All right? In this example, I'm going into global configuration mode. That's the first step. Now, what they did here is they did no access list 1 because they wanted to make sure there was no other access list called access list 1. So they just deleted it. If it didn't exist in the first place, then the command just wouldn't do anything. What does the first line of my access list do? Is it a deny or a permit? It's a deny. I am denying traffic from 192.168.10.10. What is the second line of the access list doing? I'm permitting everything else. Permit any means permit anything else. Follow along here, guys. The first step in developing and writing and creating an access list is to create the access list globally. That is the first step. But that doesn't do anything. If you just did that and nothing else, that access list doesn't do anything. The second step is to apply the access list to the interface. The second step is to apply the access list to the interface. And we do that with the IP access group command. What does the 1 represent? The access list number. What does the in represent? The direction. So I went into my router and I said under gig 00, apply access list 1 inbound on this interface. What is the effect of this access list? Host 1010 can't leave the subnet. Agree? Do you guys agree with that? Host 1010 can't leave the subnet. Everybody else can.
What do you mean by leave the subnet?
The host 1010 can't send a packet through that interface. It can talk to everybody else inside the network, but it can't leave the network. Make sense?
So in other words, you can't even get into the router yet.
Can't even get into the router. Can't telnet to the router, can't go through the router, can't get to the serial link, etc.
So would this also block telnet into the router, like you said, or SSH?
Yep. Yep. All right. Another option, and we'll look at some other configuration examples in a little bit, but another option that you have is commenting your access list. This is important, I think, because in the real world, access lists can actually be very, very long. They can have potentially hundreds of lines or thousands of lines. So by putting in comments, you can kind of help the person who's analyzing that access list understand what the purpose of those particular rule sets are. All right. Let's take a look at, well, let me give you a couple of examples. Access-list 100. Permit TCP 10.10.10.0 0.0.0.255 any EQ 80. What does this access list do? We know it's an extended ACL because it has a 100, right? We know it's a permit rule. We know it's permitting TCP traffic that comes from the 10.10.10 subnet. Going to where? The traffic is allowed to come from 10.10.10 going to anybody. So any is the destination IP address. As long as the destination port is 80. EQ stands for equal. You can do a GT for greater than, LT for less than, range, etc. So the way that you read this access list entry is exactly the way okay, I'm going to permit TCP traffic from the 10.10.10 subnet to anybody as long as the destination port number is 80. Did I specify the source port? Where would the source port go? The source port would go right here. I'll just put a couple explanation points. But how come I don't filter on the source port? I don't filter on source ports because they're usually random. Those are my ephemeral ports. All right? Here we go. Show IP interface brief. I've got fast Ethernet 00. All right? Config T. IP access dash list. Look where my options are. Extended, standard, role-based, and some other stuff. I want to create an extended access list. And I want to give it a number or a name, my ACL. This is what we call a named access list. So we don't actually create individual line entries. We create it under named access list configuration mode. Permit TCP 10.10.10.0 0.0.0.255 any EQ80. Deny ICMP any. Permit IP any. What is this access list doing? Well, we already know what the first line does because we talked about that already. What is the second line doing? Denying all ICMP traffic from anybody to anybody. What is the third line doing? Permits everything else. So actually, the first line is a little bit redundant. We didn't really need the first line because the third line would have already taken care of the first line. But maybe maybe I didn't want to allow port 80 for anybody else. I only wanted to allow port 80 if it was coming from 10.10. Well, how do I go back and insert a line? Show access dash list. There's my access list. And what do you see next to each line? You see a line number. Line 10, line 20, line 30. So how can I insert a line? Config T, IP access list. Let's go up here. And let's do 25. Deny TCP any EQ80. Do show access dash list. Now I have an extra line. I was able to insert a line. That's one of the benefits of doing named access lists. It gives you this ability to manipulate the access list line by line. So now the first command is not so useless because the first command says go ahead and permit web traffic if it comes from 10.10. But deny web traffic if it comes from anybody else. Dang it, now I want to allow ICMP. Now I want to allow ICMP. What do? Config T, go into the access list. No 20. I didn't even have to put in the whole line. I just said no 20, meaning take out line number 20. Do show access dash list, and now I see line 20 is gone. Why did router change port 80 to www? Because the router is trying to make it easier to read the access list. So for the well-known port numbers, it's going to put in the protocol name instead of the number. It's just trying to make it easier. It's actually the same thing. You could type it in as a name, or you can type it in as a number. And you can see permit, hold on, permit TCP any EQ. You can see that on the left, you see all of the names. On the right, you can see the actual port numbers. So it doesn't know every protocol, but it knows like some of the most common protocols that we'll see. And that's what we're seeing on this slide here. Show access list tells us our access list, gives us our line numbers, and then we can go in and modify, delete a line, add a line, and so on. Now, the newer version of code is very interesting. This tripped me up a little bit originally, because I can still come into my router and create an access list using the legacy method. If I'm using the modern method, I use IP access list command. If I'm using the legacy method, I just simply use access list. So let's say 10, permit IP, permit TCP any. Oops, it's a standard access list. So permit host 10.10.10.10, and then access dash list 10 permit host 5.5.5.5. Okay. So I went in here and I created using the traditional method, I created a 2-line access list. If I do show access dash list though, it shows up as a named access list using the number as the name. But if I do a show run, it shows up as a standard legacy configuration. It's really strange. So when you do a show access list, it looks like the named approach, but when you do a show run, it still looks like the legacy approach. See, this is the named approach on top. This is the legacy approach, or the older approach on the bottom. But guess what? I can go IP access list, standard 10, no 10. Do show run. Now I remove the first line of that access list. So even if you've created your ACLs using the standard method, the old method, you can manage them using the new method. It's kind of interesting. I prefer to use named access lists anyway, because quite honestly, named access lists just make more sense. Because you can actually look at the name, and you might even be able to identify the purpose of that ACL by its name. We could be spending another 2 or 3 hours talking about access lists. I promise you that. There are so many things that are going in my head right now about, oh, I need to talk about this, I need to talk about that. The purpose of this course is not to make you an expert at every level. This is an introductory course, so the purpose of the course is to introduce these concepts, give you the foundation knowledge, because a lot of these concepts involve much, much more advanced discussions. And I often find myself looking at the clock on the wall and going, man, I wish I could spend another 2 hours talking about this, because there's so much I want to tell you about it, but we can't do that. We just don't have enough time. So I know there's a lot of things about access lists that we haven't talked about, but you'll see it some other time. How do I verify my access list? We already saw the show access list command. We can also do a show IP interface command. Show IP interface will tell me if I have an outgoing or an incoming access list on an interface. All right. We also see some match conditions. This is how I was telling you that you could actually use the show access list command to see if packets are matching an access list. Notice here we see 4 hits, 8 hits, and so on. We don't know which hosts matched the rule, but we know that those rules were being matched. What if I want to secure access to my VTY lines? I can use an access list to do that as well. I create the access list like I normally would. I say, it would be a standard ACL, IP access dash list standard MGMT permit host 10, 10, 10, 10. And that's it. Line VTY 04 access class MGM10 MGMTN. So what did I do in this case? I said I created a standard access list, named access list called management. I'm allowing host 10, 10, 10, 10. Everything else gets denied automatically because of the implicit deny at the end. And then on my VTY line, I simply applied the access list inbound. So it doesn't matter what interface they're coming in from. When the telnet session or the SSH session tries to terminate on the VTY line, unless unless the host is allowed by the access list, it gets denied. We use the access class command to do that, not access group. When we're applying an access list to an interface, we use access group. When we're applying an access list to the VTY, we use access class. Alrighty, that's the end of that chapter.